Hello, hello. Hi, everyone. I hope you had a fun 4th of July weekend. We're going to go ahead and resume our materials. So this week we're doing Unit 3. So we're going to start with two sections. Well, kind of just one, because this first page is a review. And then the second page is up to page 4 is going to be our 3.1 pages. Okay. So let's start with review. First, dividing polynomials. We can divide polynomials much like how we can divide numbers using long division. When placing the dividend inside the division box, make sure there is a column for all terms even if you don't see them in the dividend. Example, divide 3x to the power 4 plus 18x to the power 3 minus x, or 3x plus 40 by x plus 7. Now notice how we have powers 4, 3, but we're missing 2. We have 1, and then we tend to have 0. So you don't have to follow this layout, but an easy way to avoid confusion is simply leaving a 0 space for the x to the power of 2. Because eventually you will get an x to the power of 2 doing this division, but it just helps you organizing. You technically don't have to do it, but I encourage you to do it. Recall, before we do this problem, regular division. First, we know that if we have 178, proposing that we divide it by 3, we're first asking ourselves, okay, how many times does 3 go into 17? It goes in 5 times. Explicitly, it's 15. But we know it won't be exactly 7, so we have a remainder of 2. And then we drag the 8 down, and we ask ourselves, okay, how many times does 3 go into 29? Well, it goes in about 9 times. Well, not necessarily 9 exactly, because we see that 3 times 9 is 27. And we're left with another remainder of 1. Typically, when we have a remainder, we write it like this: remainder over the divisor, 1 over 3. So the solution of 178 divided by 3 can be written as the quotient, what we fully factored out, or divided out, excuse me, 59 plus the remainder, oh, I wrote it, my bad, the remainder over the divisor. So just keeping that idea in mind for here. Because now we need to ask, okay, well, how many times does x go into 3x to the power of 4? Well, technically, we need to ask, okay, well, how many x's can we take out? Well, a better way to phrase this now is what times x can I make it look like 3x to the power of 4? Well, 3x to the power of 3. 3x to the power of 3 times x will indeed get us 3x to the power of 4. But what you do to this part, you have to do this part. So now I have times 7 by 3 to the power, or 3 times x to the power of 3. So that's going to be 21. And then you're left with just a power of 3. Now don't forget, when you do this product, you subtract. So here it gets a bit weird about what we subtract. So I'm going to put the whole thing in parentheses. We subtract the 3x4 by the 3, or we have the 3x4 subtracted by the 3x4. That comes out to 0. Here, we have 28x to the power of 3 minus 21x to the power of 3. It's going to be negative 3x to the power of 3. And then from here, you ask yourself, okay, well, how many times does x go into negative 3x to the power of 3? Well, negative 3x squared. X times negative 3x squared will equal negative 3x to the power of 3. Remember, what you do to this guy, we have to do the other guy. So minus 21x squared. Now remember, you're subtracting these. So we subtract a negative 3x to the power of 3. And we get a 0. And then over here, we're subtracting, here I'm going to put it down, from 0x squared. a negative 21x squared, which really means that we're kind of just adding it because it's 0 minus a negative, so plus 21x squared. I don't know why I'm doing dots, I'll do arrows. Bring this guy down, negative 3x. X times what gives me 21x squared? Well, that's just going to be 21x. So I have 21x squared, and then 7 times 21. Excuse me, I'm sorry. That's going to be, I was doing the math in my head, but then I lost track. Sorry. That's going to be plus 147x. That minus that will cancel out. Negative 3 minus 147 will be negative 150x. Bring this guy down to a 40. And then we ask ourselves, okay, well, what about x? X goes into negative 150, negative 150 times. So after doing that, we get negative 150. And then 7 times 150 gets us negative 1,050. Subtract, that will cancel out. This will add, and you're left with 1,090. Okay, so from here, what does this say? This says that when we took this whole polynomial that reads 3x to the fourth plus 18x to the third minus 3x plus 40 divided by x plus 7, this gives us our fully divided quotient, which is 3x to the third minus 3x squared plus 21. Oh, I wrote 21 backwards. 21x minus 150, and then plus the remainder, which is 1,090 divided by our divisor, x plus 7. Okay, all right. This has a method to the madness, and you're going to see it throughout Unit 3. I'm just debating on potentially showing you making this lecture a bit longer because I want to make sure that we fully understand this. Yeah, I can't help it. I think I'm going to go ahead and make this lecture a little bit longer. I apologize. Okay. Now, let's refer to this example over here. I have a point to all this, I swear. Now, let's say that you want to double check that this is the answer to this question. Well, recall that at the end of the day, this was divided by 3. So what would you do to remedy that? Multiply it by 3. So we do 59 plus 1 divided by 3. And we multiply that by 3. We theoretically should get 178 back. So we have 59 times 3, which is 177. And then we have 1/3 times 3, which is 1. So 177 plus 1 will indeed be 178. The same strategy can be utilized here. If we do x plus 7 times this whole thing, we should be able to get this full expression back. So let's do that. As tedious as it looks, this will be important, especially if you're stranded doing the division of a polynomial and you don't really have a way to fully check your answer. And just for sake of time, I'm going to go ahead and already know that because I'm multiplying this by this, I'll get the 190. Okay. Let's do all of the x's first. So I have 3x4 minus 3x3 plus 21x squared minus 150x. And then from the 7, I'm going to go ahead and put it here so it's with the 3's. I have 21x3 minus 21x squared. 21 times 21. We already did that. I think it's 147. Let me double check. Plus, or no, plus, yes, plus 147x. And then negative 150 times 7 will be negative 1050. So I know if I add, or sorry, if I add these guys, I will just get 3x4. There's nothing to really add. Here, if I combine this, I get 18x3. Here, I get 0. Here, I get only negative 3x. And then here, I'm going to go ahead and adding the 1090, I do get plus 40. And I do indeed get back my result. So just in case you're wondering, how can I double check I have the right answer if I don't have a calculator or, a chat GPT or a math solve or a simple lab? You can just go ahead and double check it like this. All right, next. SOHCAHTOA. So, I'm going to go ahead and go over this briefly. We know that if I have a triangle described here with theta, we can associate it with the acronym SOHCAHTOA, where O stands for opposite and is the opposite side of the angle. H stands for hypotenuse, which is the largest side of the triangle. And then A stands for adjacent, which is the side that's adjacent to the angle, not the largest. Using SOHCAHTOA, we can construct sine as opposite over hypotenuse, cosine as adjacent over hypotenuse, and tangent as opposite over adjacent. Here we spell the phrase so, or here we spell the phrase so, ka, toa. Now, because cosecant, secant, and cotangent are all just 1 over sine of theta, 1 over cosine of theta, and 1 over tangent of theta, respectively, we can just flip the acronym for all these guys. H over O, H over A, and then A over O. Now, does this mean that with these ideas, you can't really do much? No, it does. The only issue that we need to make sure that we know how to resolve is manipulating the triangle from our pre-cal lecture days. Okay? If you don't, or if you're unsure, I would recommend looking at the homeworks first to seeing what is presented there that you don't know that's trig related. Otherwise, reach out to me. I taught pre-cal these past 2 semesters at Tarleton, so I'm pretty familiar with the subject. And I'm also a math professor, so I'm even more familiar with the subject. All right. Let's get started with the actual new Cal 2 material. This section is going to involve a lot of strategies. The first strategy we're learning is integration by parts. The formula for integration by parts comes from the product rule. Say you have this setup where you're taking the derivative of u times v, where both u and v are functions of x, and you want to go ahead and do this integral. Now, technically, if you do this step first, it's u plus v prime plus v plus u prime. And technically, the derivative and the integral cancel each other out. Well, what I could do is I could subtract this integral from both sides. And after subtracting this integral from both sides, we have a technicality. This area right here and this area right here have a substitution trick in mind. This substitution trick, it does have a bit of a proof to it, but you can go ahead and skip that part of the proof and simply just notate it as the derivative of u and the derivative of v, respectively. Afterwards, you can go ahead and reverse this to where it's this guy on the left and this guy on the right. Now, the gimmick here is that you've just made a formula where u and v are functions of x. What you want u to be is you want u to be something that's derivative can make the expression disappear. What you want dv to be is a common / known antiderivative. The complicated thing about this formula is being able to correctly identify both u and dv. It will not always be clear, and sometimes we'll make the wrong choice. If we do make the wrong choice, we can always go back and try a different set of choices. This is my strategy for knowing what what to make as u and what to make as v. But I did include, and in the group work, we're gonna see we're gonna see these problems 3 and 4 be a bit annoying. So let's start. We have number 1 that reads the integration of x times e to the x. Now remember the strategy I taught you, or I told you, not taught you yet, I'm teaching you right now, is something that as you take derivatives can disappear. Well, we know that if I take the derivative of x, it will disappear into just a constant. So let's go ahead and make u that derivative of x, and make dv, which is the derivative of a function, be e to the x dx. Now, if I take the derivative of u, I get just 1 dx. And if I take the antiderivative or the integration of e to the x, we know that's a very known antiderivative. It's just e to the x. Now we're going to go ahead and plug and play this formula. So if I labeled this correctly, u times v comes out first, so x times e to the x, and then minus the integral of v which is just e to the x, and then du, which is 1 dx, which I'm just going to go ahead and skip the 1 and do dx. We definitely know this integral. This integral is just e to the x. And then you have the potential of adding plus c. And that's your answer. X times e to the x minus e to the x plus c. Now, remember that at the end of the day, right, if you want to prove that this guy and this guy equals, you have to remember the idea of its derivative. Let me see. I also could wait before I do that. I want to say, um, you could also. I don't think it'll matter just yet, but you could factor out the e to the x. Mm, let's go ahead and do the derivative. So I want to do the derivative to show my example. Yeah, right, yada, yada, yada. And I'm going to do x minus 1 e to the x. I'm going to go ahead and do the derivative of this. Okay? Well, we have this first guy. So what's the derivative of this first function? It's just going to be 1. And 1 times e to the x. And then you add it to x minus 1. And you take the derivative of the second guy, e to the x, which was just e to the x. You're going to distribute just a little bit. Oh, and we know derivative of a constant will be 0, by the way. And you'll get these e dx cancel out, and you're left with x e to the x. And look, you got back the exact same guy. So don't forget about this method, because we talked about this method in our previous lectures as well. If you ever want to double check your answer, simply perform the derivative of this. Now, granted, the reason why I was like, let me go ahead and round it up is because this is going to be a bit annoying if you don't. Maybe it wasn't actually, maybe I overthought it, but either way, if you didn't separate it, look, I'll do it just quickly. If you didn't separate it, the derivative of this guy is just going to be, prime, sorry. It's just e to the x plus x e to the x, and then the derivative of this is just e to, oh, so I guess it was the same thing. Oh well. Well, either way, you have multiple ways to solve this. The gimmick is that we're showing that a derivative is a step forward and integration is a step back. So if we're going a step back, then going a step forward should land us in the same spot. All right, let's increase the difficulty slightly and go to number 2. Number 2 reads the integration as x is to the power of 2 times e to the x. Now here, I have a technical issue. The issue is that x to the power of 2 does not disappear after one derivative. And e to the x does not disappear after doing a derivative. However, with number 1 being a sort of hint, we do have a pretty good idea that x squared will disappear. You just have to take more than one derivative. Let me explain. So you have u be x squared, and you have du be that derivative. So 2x dx. Let dv be e to the x dx, and then let v be e to the x. Performing this substitution, you'll have u times v, which is x squared ex, and then minus the integral of v e to the x, and then now you have to deal with du, and du reads 2x dx. Well, we can mess with this a little bit, not a whole lot of it, but a little bit. X squared ex minus 2 integration ex x dx. I'll put the x over there. So what do you think we do here? Well, we are going to take another integration by parts method. So real quick, let me see. How do I say this? I don't want you guys to worry too much about on a test doing multiple integration by parts. I will probably put at least at the moment, I don't have the test made yet, but I will probably put at least one question where there'll be at most two separate integration by parts. But just keep that in mind for levels of difficulty. Now, levels of notation, there's not really a concise one. I've seen a bunch. You can do U and V. Some people like to do just two different letters. Um, some people like to do capital letters, and some people, I don't know if I said, but some people like to color code. I obviously like to color code. I don't know if you can tell. But I'm also gonna do a different way. Some people like to use capital letters, so I'm gonna use capital letters. So I have capital U, D, capital U, D, capital V, and V. So similar ideas happening here, and I'm basically gonna copy and paste this method: x dx, ex, ex dx. And over here, you replace this whole thing with, or here, I'm gonna do another, oh, I dropped my pen, hold on. You have x squared ex minus 2 and then parentheses x times v. I'm sorry, wait. Oh, I accidentally wrote the dx here. I don't have whiteout. Oh no. Oh, we're just going to go with reliable. Scratching it out. Okay. U times v was just x e to the x, and then minus the integral of, of v times du. So ex dx. Which we already know that this guy in full, we have x squared ex minus 2 parentheses xex minus ex and then plus c is our answer of this integration by parts. It's the one we got in the beginning. But the last step we need to do to get the full answer, because this kind of answer is already more or less full, is multiplying that 2. So if we multiply that 2, we should get a full answer of x squared e to the x minus 2x e to the x minus e to the x. And then you could do negative 2 plus c, but we know it's just an arbitrary constant, so you can leave it as plus c. And maybe you write a star here if you want, just to note that it did change, but not by a lot. And that'd be your answer. All right. Next, we have an issue. Not only do we have a function within a function, but within the function within a function, you could argue, well, let's use substitution, just classic substitution. Well, there is no derivative of either sine or ln that appears within this integral. So sometimes what we do with integration by parts, here, I need to write this. Sometimes integration by parts makes the problem more legible. Let's start. So let's take u to be this whole thing. Sine of ln of x, and let's take dv to be dx. We already know that the derivative of the integral of this must be x itself. Here, we just do the derivative. Now, derivative here is just classic chain rule. You're doing sine's derivative first, which is just cosine of ln of x. And then you do derivative of what's inside of that, which is just 1 over x times 1 over x. And then because of this notation, you're multiplying it by dx. Then after this, you do the integration by parts. So we have u times v, which is just sine ln of x times x, which at this moment, it looks ugly. I will not sugarcoat it. So you may think, well, that doesn't really make it look more legible. What the heck? Well, remember, you can write any expression down. The difficulty that was presented to us at first is that the integral had the ugly thing inside of it. And now let's write the new integral here. So minus the integral of v, which is just x, times du, which is cosine of ln of x times 1 over x dx. Okay? So then from here, you're going to go ahead and simplify. Well, what can you really simplify from here? Well, from here, what you can simplify is the x and 1 over x. Oh, that's interesting. Um, there's a missing. Hold on, give me a second. Let me cook. I think I have a missing question. No, I don't. Okay. Well, Okay. I promised it wasn't Method's madness, but right now it just looks like madness. So let me go ahead and keep it going because technically I lied right now. This does not look any prettier. In fact, as I rewrite this, you'll see that you have the same sort of integral cosine of ln of x and then dx. So you have the same sort of integral. The only difference here is that we've written cosine instead of sine. So what does that mean for us to do? Well, that comes to the next part, which I technically wanted to do here, but I'm gonna go ahead and say that I may just tackle it in the group work. Or I may just leave it alone. I'll think about it. Okay. Because sometimes what will happen is sometimes integration by parts make the problems more legible. And that's just true. Sometimes we just want to take a generic integration by parts and see what even happens to begin with. But sometimes we want to take an integration by parts and you want the integral to appear again. So what does that mean? Well, let's go ahead and use this strategy combined with doing another set of integration by parts. take the whole thing, cosine ln of x, and then take the derivative of the whole thing. So negative sine ln of x times the integral ln of x, 1 over x. I mean integral, the derivative, and then times dx. dv will just be dx, and v will just be x. From here, we can go and do this integration by parts, which reads u times v, which is just x times cosine of ln of x, and then minus the integral of v with this whole thing. So I'm going to go ahead and I'll write it out in full. Negative sine ln of x, 1 over x dx. Not only do the negatives become positive, that will cancel out, and you're left with this final version plus the integral of sine ln of x dx. Now, I'm going to ask you a little bit of a wink of a trick question right now. Where have we seen this before? And can anybody tell me on the screen where we have seen this before? Right here. It's the same exact thing printed out. In fact, if we wrote our expression fully, including distributing the negative, we have the integration of sine of ln of x dx is equal to first x sine ln of x minus x cosine ln of x, and then minus the integral sine ln of x dx. And remember, we're technically solving for this integral. So what if I just solve for this integral as if it was its own variable? If it's its own variable, then I literally can just add it to one side. So it's just 2 integral sine ln of x dx is equal to x sine ln of x minus x cosine ln of x, and then just divided by 2. The integral of sine of ln of x dx is equal to x over 2 times sine ln of x minus cosine ln of x. And then technically, because this is an integral result, we do want to add the potential of a constant appearing. And that is the full answer. Now keep in mind, this was obviously a chink and nod, and it wasn't us truly integrating it. Does that mean it was improbable? No. It's just a different way to look at it, which still makes the integration by parts valid. Okay. I think I'm gonna let the typo be. Or not typo. It's because like I was going too hard with the flow, and I realized that there was technically like I wanted to do a bit more of a setup, but I think I'm actually just gonna let your homeworks be that practice. So keep that in mind, okay? If you're using an AI or a tutoring system to help you, that's technically fine as long as you're learning from it. If you're not learning from it, we've got issues, okay? But if you're just, using it, like, honestly, that's also, valid, but you just need to make sure you're doing what you need to do. Okay, I want to practice one more of these with you with number 4. Okay, okay. So let's go ahead and start. We have this whole integral, and we can't use the trig before because we know that this derivative will repeat forever, and this derivative will repeat forever. So let's make the problem more legible and put the whole thing into integration by parts. E to the x sine of x, and then the other part will just be dx. This will be x, and this will be a product rule, which is e to the x times sine of x plus, I'm going to put this all in parentheses, by the way, um, e to the x cosine of x, and then all times dx. All right, let's go ahead and set up the integration by parts. We have x e to the x sine of x is equal to minus the integral of x times x sorry, e to the x sine of x plus or dx. Hold on, I'm getting even confused with notation. Let's go ahead and just separate this already. So that's one bubble. Then minus integral x e to the x cosine of x dx. Now from here, we have a technical issue. The technical issue is that we have actually done opposite of what we wanted to do. And what we have done is we have made this integral much harder. However, what we're going to attempt to do, so this is, wait, let me write that this is a dead end. But what we're going to attempt to do is we're going to take one of the trig functions. We have just seen an example where the trig function within the integral repeats itself. So, what if instead I take u, this new u, right, nu for the whole thing really, to be sine of x, and dv to be e to the x dx. And let's see if I can make that trig trick work to my favor. If I do derivative of sine, that's just going to be cosine of x dx. And if I do derivative, or the integral of this, it'll be e to the x. Let's make that happen. We have e to the x sine of x minus the integral of e to the x cosine of x dx. From here, I'm going to go ahead and do the similar by where I make u to be cosine of x and dv to be e to the x dx. In that case, I'm still copying. Oh, wait, let me do capitals, excuse me. I'm still doing a similar du, which have negative sine of x dx. Then the v will be e to the x. e to the x sine of x minus the parentheses of u times v, so e to the x cosine of x minus the integral of e to the x negative sine of x dx. Then from here, I'm going to distribute and simplify already the full. Oh, I forgot a color code. Well, this whole thing was representative. This work for integration by parts. I hope that's obvious. Okay, we have e to the x sine of x minus e to the x cosine of x. And then I'm going to do whole minus, because that's a triple negative. I miscounted, so negative times negative will still be negative. The integration e to the x sine of x dx. Now, where do we see this guy? In this problem. Let's write out the full setup. Here. If I take it to one side and divide by, since I'll have two of these integrals, my final answer should be e to the x sine of x minus e to the x cosine of x divided by 2 plus a c. All right, now keep this in mind. There's versions of this where you can, take out the E. You don't have to, even though I took out the X for the previous ones. I'm kind of contradicting myself, but it's nothing too crazy. Yeah, because remember we add, and then we divide by 2, get the answer. Similar thing happened here, so don't worry too much about it, but yeah. Um, okay, so what I'm struggling with right now is the fact that I'm not seeing your faces as you're watching this video. Because this isn't a classroom, right? This is an online video. Or it's a classroom, right? But it's an online classroom, is my point. So we need to make sure that we got this, guys, okay? And the worst part is that you can't even see my face. You just see a moving bear right now. But I promise tomorrow, by the time you see this, um I will have a regular camera showing my face. Um, let me know if you guys have any questions, guys, okay? Um, I'm gonna do the group work video soon after this, so I'm gonna try to make that to where it talks about this second point that I accidentally skipped over here. Okay? All right, let me know if you have any questions, and I will see you all in the next one. Bye bye.